Somewhere in a Martian valley, the ground looks like it was carved by insects. It wasn't. NASA's Curiosity rover just found something scientists have never seen before. And even now, they don't fully know why it's there. In June of 2026, a robot the size of a small car pointed its camera at the ground on another planet and sent back an image that made its own science team stop and stare. Thousands of six-sided shapes, pressed into solid rock, fitting together edge to edge like the inside of a beehive built for no one. They didn't stop at the edge of the frame. They kept going, across a valley floor, up the side of a small hill, in every direction the camera could see. It is the largest field of this kind Curiosity has ever recorded in 14 years on Mars. Here is the question that opens this story, and the question we will keep circling back to. What actually carved these shapes into an alien landscape? And why, after 14 years of driving across Mars, did the rover find nothing like this until now? That second question matters more than it sounds. This isn't a rover's first look at strange, geometric ground on Mars. It's seen small patches of shapes like this before, scattered here and there, never explained with total certainty. But nothing at this scale. Nothing that turns an entire valley into a mosaic. There's a name for this place now. The science team calls it Valle Grande. Big Valley in Spanish. And somewhere inside that valley, Mars has been quietly building a structure that looks less like erosion and more like architecture. To be clear from the outset, nothing about this discovery suggests anything built by intelligence, ancient or otherwise. Every scientist involved describes this as a natural geological pattern. But natural doesn't mean boring. The process is capable of producing a shape this precise, at this scale, on a planet this different from our own, are exactly the kind of processes scientists need to understand if they're ever going to answer the bigger question hanging over the entire Mars program. Did this planet ever support life, even briefly, even microscopically, before it dried into the world we see today? We're going to walk through exactly what NASA's Curiosity rover found, what scientists actually know for certain, what remains genuinely unexplained, and why a pattern of cracks in ancient rock might be one of the most important clues we have about whether Mars was ever alive. This is not a story about hidden alien ruins. It's stranger than that, in a quieter way. Because the real explanation, whatever it turns out to be, is written in the chemistry of a planet that used to have water and now doesn't. And this isn't even the first time Curiosity has driven past something that didn't seem to belong. Over 14 years, the rover has photographed golf ball-sized rocks made almost entirely of iron and nickel. Visitors from deep space that struck the Martian surface long before any robot arrived to notice them. It has found crystals of pure sulfur sitting in the open, with no obvious source. So when this science team says a honeycomb field the size of a valley caught them off guard, that's not marketing language. That's 14 years of expertise, genuinely surprised. Let's start with what we're actually looking at. On August 5th, 2012, a spacecraft carrying a 1-ton, 6-wheeled rover slammed into the Martian atmosphere at more than 5 kilometers per second. It slowed itself with a heat shield, a parachute, and finally a hovering rocket-powered crane that lowered the rover gently onto the surface on cables, then flew off and crash-landed a safe distance away. That rover was Curiosity. It landed inside Gale Crater, a massive impact basin roughly 150 kilometers across, chosen specifically because orbital images showed layered rock and a central mountain. Signs that water may have shaped this place a very long time ago. Curiosity's mission was never to look for aliens walking around. Its job was narrower, and in some ways more powerful, to determine whether ancient Mars ever had the conditions necessary to support microbial life. Not to find life itself, to find out whether the ingredients were ever there. Over more than 14 years, Curiosity has answered that question with a clear yes. It found rocks that could only have formed at the bottom of a lake. It found the chemical fingerprints of ancient, gently flowing water. Not a flash flood, but a long-lived, calm environment, the kind that could have supported simple life if any existed. It found the basic chemical building blocks life would need: carbon, hydrogen, Oxygen, nitrogen, sulfur, phosphorus. All present. All in the right rock. Mars, in other words, was once a place water could pool, and where water pools, chemistry gets complicated. Sometimes complicated enough to matter. None of this comes from guesswork. Curiosity carries a small laboratory's worth of instruments on its 1-ton frame. A camera-mounted laser called ChemCam can vaporize a pinhead-sized speck of rock from up to about 7 meters away and read the resulting flash of light to identify exactly which elements are present. A drill on the end of its robotic arm can bore into solid stone and feed the powder into an internal oven where an instrument called SAM, Sample Analysis at Mars, heats it to nearly 1,000 degrees Celsius and studies the gases that escape. This is how the rover doesn't just see something unusual. It can prove, chemically, what that something is made of. That toolkit has already turned up genuine surprises before. In 2014, not long after landing, Curiosity rolled past a 2-meter iron-nickel meteorite the team nicknamed Lebanon, a chunk of some ancient asteroid's core sitting exposed on the Martian surface. In 2016, it found a smaller one, golf ball-sized, nicknamed Egg Rock. In 2023, another one, nicknamed Cacao, about a foot across. Each time, ChemCam's laser confirmed the same thing. Metal that could only have come from beyond Mars, from asteroids that broke apart long ago, their fragments scattered across the solar system and some of them landing here. So when scientists say the ground in Valle Grande looks unusual, they're not speaking casually. They're speaking as people who have spent over a decade cataloging what normal Martian rock looks like. And this broke the pattern. The rover has been slowly climbing the base of Mount Sharp, the layered mountain at the center of Gale Crater, since 2014. Each layer it passes represents a different chapter of Martian history. Older rock, lower down, younger rock, higher up, like the pages of a book written in stone. Scientists read those layers to reconstruct how the crater's lake dried out, how the climate changed, and how the planet eventually became the cold desert we see today. Valle Grande sits along that climb, and it's here, in the middle of that long geological record, that the honeycomb field appears. One detail worth holding on to for later. Curiosity has found strange, unexplained things before. Bright, glassy rocks. Metallic meteorites sitting exposed on the surface. Pure sulfur crystals that had no obvious explanation when they were found. Each time, the mystery eventually gave way to an explanation grounded in ordinary physics and chemistry. Nothing supernatural, nothing that needed a cover-up. Just Mars, being more complicated than expected. Keep that pattern in mind. It matters for how we should think about what comes next. There's one more piece of context worth having before we go further. Scientists believe Gale Crater once held an actual lake. Not a myth, not an inference from a single rock, but a body of water that likely filled and drained multiple times over millions of years as Mars's climate shifted. Mount Sharp itself, the mountain Curiosity has spent a decade climbing, is thought to be built largely from sediment that settled to the bottom of that lake, layer after layer, before wind erosion carved away the surrounding material and left the mountain standing alone in the middle of the crater. Every rock Curiosity examines on that climb is, in a sense, a page torn from the biography of a lake that no longer exists. On June 19th and 20th, 2026, the 4,930th and 4,931st Martian day of the mission, known as a sol, Curiosity parked itself in Valle Grande and did something it does periodically. It spent 2 full days taking pictures in every direction, slowly rotating its mast camera to build a complete 360-degree panorama. It captured 340 individual images. Back on Earth, the science team stitched them together into a single, continuous view. What that panorama revealed surprised even scientists who have spent years staring at Martian terrain for a living. The ground was covered, edge to edge, with small polygon shapes. A honeycomb texture, each individual cell only about 4 to 8 centimeters wide, roughly the size of a coin to the size of a fist. Geologists call these polygonal fractures, and they didn't just sit flat on the valley floor. They wrapped around the base of a small rock formation nicknamed miraflores, a boot about 6 meters tall, capped with a thick layer of loose sand. Climbing partway up its sides, as though the pattern didn't care about the terrain's shape at all. The mission's project scientist, Ashwin Vasavada of NASA's Jet Propulsion Laboratory, has described the discovery as genuinely surprising, even to a team that has seen 14 years of Martian landscapes. The team has measured the shapes and analyzed their chemistry carefully, hoping the data itself holds clues to how the pattern formed. Building that panorama wasn't a quick snapshot. Curiosity's masked camera, mounted about 2 meters off the ground, had to be pointed, focused, and fired in a careful sequence. A slice of sky here, a slice of ground there. Over 2 separate Martian days, before the images could even be transmitted back across the vast gulf of space separating Mars from Earth. Only once the full set landed in mission control could the imaging team begin stitching all 340 frames into the single, continuous view that revealed the true scale of what Curiosity was standing on. No single photograph could have shown it. It only became visible once the pieces were assembled, which is part of why nobody saw this coming until the panorama was complete. Here's what makes this different from previous sightings. Curiosity has photographed small patches of polygon-shaped cracking before, scattered here and there across its long drive. Scientists never made much noise about those. A few square meters of cracked ground isn't unusual on any rocky planet. But Valle Grande isn't a patch, it's a field. It's the largest expanse of this pattern the mission has ever documented in one place, and it appears to extend well beyond what the rover's cameras alone can capture. That raises the second curiosity loop we opened earlier. Why here? Why now? After 14 years and thousands of images, does this pattern suddenly show up at massive scale? Is Valle Grande sitting on some kind of unusual geological boundary? A place where ancient water behaved differently than it did elsewhere in the crater? Or is this simply the first place the rover has driven through where the right conditions for large-scale cracking happen to survive, undisturbed, for billions of years? Scientists don't have a confirmed answer yet. What they have is a working method. Study the shapes, study the chemistry inside them, and compare it to how similar patterns form on Earth. That method is already underway. The science team has started pointing ChemCam directly at individual fractures within the honeycomb field, reading the chemical composition locked inside each crack. Looking for the specific mineral signatures that only form in the presence of liquid water, versus the signatures left behind by pure temperature-driven stress with no water involved at all. It's slow, patient work, done one laser pulse at a time, on a planet where sending a single command takes several minutes just to arrive. Which brings us to the strangest part of this story. Because Mars didn't hand scientists just one mystery in Valle Grande. It handed them two. Scattered across the honeycomb field, mixed in among the pale, cracked rock, the rover's cameras picked out something else, dark rocks. Not part of the honeycomb pattern itself. Sitting on top of it, or wedged between the fractures, clearly distinct from the lighter material around them. This is where the story stops being simple geology and becomes an open scientific puzzle with three competing explanations, none of them confirmed. The first possibility. These dark rocks are native Martian material that originated much deeper underground and somehow made their way up to the surface. What scientists describe as material that floated up through the rock layers over time, exposed as wind slowly eroded the softer stone around it. The second possibility? These rocks are ejecta, debris violently thrown across the Martian surface by an asteroid or comet impact somewhere else on the planet, then landed here, kilometers or even hundreds of kilometers from where the original impact occurred. The third possibility is the strangest one to say out loud. And yet it's a completely ordinary occurrence in space. Some of these rocks might not be from Mars at all. They might be meteorites, fragments of asteroids or other bodies that fell from space and struck the Martian surface directly, the same way meteorites occasionally strike Earth. NASA has been direct about the uncertainty here. The agency itself has stated, in describing this find, that a still unresolved question is whether these dark rocks floated down from higher in the surrounding rock layers, were ejected from a distant impact, or are meteorites from beyond Mars altogether. That is not evasive language. That is what real, honest, scientific uncertainty sounds like. There is one clue pointing in a specific direction, though it isn't proof. Some previously studied dark rocks in this same region were found to contain nickel, a metal that shows up commonly in meteorites because it's abundant in the metallic cores of asteroids, but far less common in typical surface rock. That doesn't confirm an extraterrestrial origin for every dark rock in Valle Grande, but it keeps the meteorite explanation firmly on the table, alongside the other two. And this isn't a theoretical possibility. Remember Lebanon, egg, rock, and cacao. The iron-nickel meteorite's curiosity has already confirmed at other points along its journey. Those finds prove that space rock genuinely does land here, survives the fall, and sits on the surface for scientists to find, sometimes for millions of years before a rover happens to drive past. So when dark, out-of-place rocks turn up, scattered through the honeycomb field, the science team isn't reaching for an exotic explanation. They're checking against something Mars has already shown them, more than once. What they don't yet know is whether Valle Grande's dark rocks belong to that same category, or whether this time the ordinary answer is the less exciting one, material from Mars itself that simply eroded up from below. This is the third curiosity loop of our story. Are the dark rocks scattered across this alien honeycomb field pieces of Mars itself, or genuine visitors from somewhere else in the solar system, sitting in plain sight, waiting to be identified? As of now, the evidence does not yet prove which explanation is correct, and it may turn out to be some combination of all three. There's a reason this particular question can't be rushed. Confirming a meteorite isn't as simple as noticing a rock looks dark or out of place. Plenty of ordinary Martian rock looks dark too, depending on dust cover and lighting. It takes ChemCam's laser, fired directly at the rock's surface, reading the exact ratio of iron to nickel to phosphorus in the vapor it produces. Only that kind of chemical fingerprint can separate, "This looks unusual," from, "This is definitively not from Mars." Until the science team runs that analysis on the specific dark rocks scattered through Valle Grande, the honest answer stays open. Put those two mysteries together: the scale of the honeycomb pattern and the unidentified dark rocks scattered through it, and you start to understand why the science team called this discovery genuinely breathtaking, rather than just another interesting rock formation. Two open questions, in the same square kilometer of Martian ground, both tied to the deep history of a planet that used to have water and might once have had the chemistry for life. Let's talk about what scientists actually think is happening here, starting with the explanations that have the most evidence behind them and moving toward the ones that are still speculation. Most supported: mud cracks from drying sediment. This is the explanation with the deepest evidentiary backing, because curiosity has confirmed it before, elsewhere in Gale Crater. Some polygon patterns the rover previously examined clearly began as ordinary mud cracks. The same process you can watch happen in a drying puddle on Earth. Wet, fine-grained sediment settles at the bottom of a lake or seasonal pond. As the water evaporates, the sediment shrinks. Shrinking material under tension cracks in a very specific, very geometric way. And because the stress pulls evenly in multiple directions, the cracks tend to form hexagonal, honeycomb-like networks rather than random lines. It's the same physics behind cracked drought lake beds on Earth, from Death Valley to the salt flats of Bolivia. If this explanation holds for Valle Grande, it would mean this valley once held standing water long enough for fine sediment to accumulate and later dry out completely. A direct, physical record of a lake or pond that no longer exists. The scale of the pattern is what makes this version of the story so striking. A cracked puddle in your backyard covers a few square meters. Valle Grande's honeycomb field covers ground the rover can't even see the end of. If drying water shaped all of it, that implies a genuinely large body of water once sat in this exact valley. Not a puddle, but something closer to a shallow lake, evaporating slowly over what may have been years or centuries, not days. Well supported. Thermal contraction cracking. The second leading explanation doesn't require standing water at all, just extreme temperature swings, which Mars has in abundance. Air temperatures at Gale Crater routinely swing more than 50 degrees Celsius between afternoon and the hour before dawn, and the ground itself, which heats and cools even faster than the air above it, swings through an even wider range. Repeated cycles of that kind of heating and cooling cause rock and sediment to expand and contract over and over until the material eventually fractures along predictable lines. Very similar to how permafrost cracks into polygon patterns in Earth's Arctic tundra, a process geologists have studied for decades. On Mars, without a thick atmosphere to hold onto heat the way Earth's does, these temperature swings happen every single day for billions of years. Given enough time, that alone could carve a landscape into a honeycomb. Unlike the mud crack explanation, this one doesn't need Valle Grande to have ever held a lake at all. It only needs rock and time, both of which Mars has in abundance. That's exactly why scientists can't simply pick their favorite explanation and move on. Two very different Martian pasts, one soaked in ancient water, one bone dry and simply enduring billions of freeze-thaw cycles, could, in principle, leave behind a strikingly similar pattern on the surface. Telling them apart requires looking past the shape of the cracks and directly at the chemistry trapped inside them. Plausible, still under investigation, compression from burial. The third explanation is more specific to Mars's deep geological history rather than its current climate. As sediment settles and gets buried under new layers over millions of years, the weight above it compresses what's underneath, squeezing trapped water out of the rock. That process can also generate fracture networks with a geometric, polygonal character. But it happens deep underground, meaning we'd only see the pattern today because billions of years of wind erosion have since stripped away the layers that used to sit on top, exposing what was fractured far below the surface long ago. Most speculative, a combination of all three, varying across the valley. NASA's own scientists have been careful not to commit to a single cause. It's entirely possible, maybe even likely, that different parts of Valle Grande formed through different processes at different points in Martian history, and the rover is looking at a landscape that layered multiple explanations on top of each other over billions of years. Distinguishing between them will require exactly the kind of detailed chemical and structural analysis the science team is currently running. Measuring the mineral composition inside individual cracks, checking for the chemical signatures water leaves behind versus the signatures pure temperature cycling leaves behind. It's worth being honest about how science actually works here, rather than pretending certainty exists where it doesn't. A documentary can rank explanations by how much evidence currently supports them. It can't declare a winner before the data does. Right now, mud cracks and thermal cycling both have real, physical precedent elsewhere in Gale Crater and on Earth. Compression from deep burial is geologically reasonable but harder to confirm from the surface alone. And the possibility that Valle Grande is a patchwork of more than one process, changing subtly from one end of the valley to the other, remains entirely on the table. That's not a disappointing answer. That's what an honest one sounds like, 4 months into studying a discovery this size. This is where we can finally answer the first curiosity loop we opened at the very start. What carved these shapes into the ground? The honest answer, as of today, is that scientists are still investigating. But the leading, evidence-backed explanation is some combination of ancient drying water and billions of years of relentless temperature cycling, with deep burial and compression as a real but less certain contributor. Not aliens. Not artificial structures. Something arguably more remarkable. A physical record of Mars's slow transformation from a wetter world into the desert it is today, written directly into the shape of the rock. It would be easy to watch a video about cracked rock on Mars and wonder why any of this deserves attention. Here's why it does. Earlier in its mission, Curiosity drilled into a billion-year-old lakebed rock called Cumberland and found the largest organic molecules ever identified on Mars. Long carbon chains that scientists believe are likely fragments of fatty acids, the kind of molecule that forms cell membranes in every living thing on Earth. To be clear about the uncertainty here, scientists cannot yet determine whether those molecules were produced by biological processes or purely geological ones. Fatty acid-like compounds can form both ways, including through non-biological chemical reactions at hydrothermal vents. Both remain possible. What the discovery does confirm, without question, is that ancient Mars had the basic chemical ingredients life would have needed, if it ever existed there, and that Martian rock is capable of preserving fragile organic molecules for billions of years. The honeycomb field in Valle Grande connects directly to that larger story. Every polygon, every crack, every fracture pattern is a physical record of exactly how water behaved in this specific place, how long it lasted, how it dried out, what it left behind. Understanding whether this pattern formed from a shallow lake, from temperature cycling, or from deep burial tells scientists something concrete about Mars's water history in a location they haven't studied this closely before. And places where water lingered longest, chemically speaking, are exactly the kinds of places most likely to have preserved any signs of ancient microbial life, if it ever got started. There's also a more immediate, practical reason to care. Curiosity is still climbing. Mount Sharp still has layers above it that no rover has ever examined up close, each one a further chapter in the story of how Mars dried out. Every strange discovery along the way, this honeycomb field included, helps mission scientists build a more accurate map of where to look next and what instruments to prioritize when they get there. Understanding Valle Grande properly today could directly shape which rock the rover decides to drill into a year from now. That's the through line connecting every strange thing Curiosity has found across 14 years on Mars. The sulfur crystals, the metallic meteorites, the ancient lakebed minerals, the organic molecules, and now this vast field of honeycomb-shaped rock. None of them are, on their own, proof of life. Each one is a puzzle piece, and scientists are slowly assembling those pieces into the clearest picture we've ever had of what Mars actually used to be. The dark rocks scattered through the honeycomb field remain unidentified. The precise cause of the polygon pattern remains under active investigation. NASA has not claimed otherwise, and neither should we. What we can say with confidence is that a small robot, alone on another planet, spent 2 days quietly photographing the ground beneath its wheels, and in doing so, uncovered a landscape that raises more questions than it answers. It's also worth remembering the scale of what's actually happening here. A car-sized machine, launched in 2011, has now been driving across another world for longer than some viewers of this video have been alive. Climbing a mountain nobody has ever stood on, drilling into rock nobody has ever touched, sending every image and every measurement across the vast distance separating Mars from Earth so that people on a different planet entirely can try to understand what happened here billions of years ago. Valle Grande is just the latest page in that record. It almost certainly won't be the last strange thing Curiosity finds before its mission eventually ends. Somewhere in that valley, the ground remembers something the rest of Mars has already forgotten. We just haven't finished reading it yet.